everyone. This is Jeff Wilkerson, Professor of Physics at Luther College. What we're doing today is finishing working a problem for the Engineering Science Physics 150 course that we were working on. Just a little bit ago, we were solving this problem, and we got it all set up, and we want to make sure we understood why we set everything up the way we did, and then we can go ahead and solve it all the way through if we want to here. So that's what this is. This is a statics problem. This is a that you might encounter in an introductory physics course or an engineering science course like the one we're working on here, which is both of those things. So we had this beam, and this beam had a length of 3.5 meters, and I think it was 50 kilograms. That's what we're going to call it here anyway. 50 kilogram beam, and it had a hinge here, and there was a cable that was holding it. We wanted to know what the tension in the cable was. So what the cable's doing, we're thinking about this. We got this beam, we got this cable that's pulling it against the wall. What keeps it from going through the wall is that there's a reaction force, is that there's a hinge force that pushes back in the opposite direction, or a normal force with the wall that pushes back in the opposite direction. But the tension also pulls up on the beam, and it keeps the beam from sagging down and rotating down this direction or falling. And so there's a hinge force there in the y direction, and there's a tension in the y direction, and there's the weight of the beam, and there's the weight of this bag of goodies that's trying to pull this thing down. So we set up our usual statics equations here. We are to say that the sum of the forces in the x direction has to be 0, and the sum of the forces in the y direction has to be equal to 0. And also then, we're going to calculate the moment. We could calculate the moment. We could calculate the sum of the moments around any point we wanted to, or the torques, if you will, if you're thinking about it that way. Same thing. So physicists might think about these as torques, or engineers think about these as moments. We're going to calculate the sum of the moments around this point. We could pick any point we wanted, but we want to get rid of those hinge forces because we're not interested. We're asking the question, what's the tension in the cable? We'd like to stay away from these hinge forces if we don't need to know them. And so we're going to see if we can get away with that. So then we want to say the sum of the moments that tend to cause counterclockwise rotations are going to be equal to the sum of the moments that cause clockwise rotation. The moments, as we had talked about in class, the moments that cause counterclockwise rotation look like the tension in the cable, and we don't have to worry about the hinge force and what direction it's going, because we got rid of that. So it looks like the y component of the tension in the cable is causing this to want to do a counterclockwise rotation. Now, we could figure out what this angle is and figure out this in terms of t times, do some trigonometry right here. But let's just call this the y component for the time being. And we'll do our trigonometry at the end. We could do it at the beginning, but we won't. So it looks like t sub y is causing a counterclockwise rotation. And t sub y, you need a moment arm. How far is it acting away from where we decided to calculate the moments around, and that's 3.5 meters. So we have 3.50 meters. And that's it. That's what we've got for what's pulling this, causing this thing to want to rotate this way. Weight of the beam and weight of the bag are what's trying to cause it to rotate down the other direction in the clockwise direction. So this has to be equal to the weight of the bag, which is 17 kilograms, times 9.81 meters per second squared, times the moment arm, which is 3.50 meters, plus the weight of the beam is going to cause it to want to rotate that direction too. And the weight of the beam is going to be 50 kilograms times 9.81 meters per second squared times 1.75 meters. 1.75 meters is half the distance out here. This is the center of mass of the beam. So the mass of the beam acts at the center of mass to cause this rotation. So we figure we'll pick the center halfway out. This is what we want to do here, is to say we can't put 3.5 meters because that would act like all of the mass of the beam was out here causing this torque, causing this rotation. And it's uniformly along there, so we pick the halfway point. Think about it this way. Think of the mass that's out here is doing a lot. the piece of the beam that's out here is doing a lot to cause it to want to rotate. The beam around this point, the beam that's right here is the little mass of the little piece of beam that's right here next to the hinge is doing almost nothing because it's so close in there. The moment arm is 0 for this end of the beam. It's 3.5 for this end of the beam. It averages out to be 1.75 right there in the middle. If the beam weren't uniform, if the beam had a density variation across there or a shape variation that it got wider as it moved out this direction, we'd have to do something a lot more. But this is where we are right now with this uniform beam. So this is all great. We know everything in that equation. We can say T sub y is equal to 17 kilograms times 9.81 meters per second squared. And the 3.5 comes around. We're going to divide it through on the other side. Let's go ahead and do it. I was gonna be fancy and not do it, but let's do it. Plus 50 kilograms times 9.81 meters per second squared times 1.75 meters, all divided by 3.50 meters. All I did was divide the 3.5 out to the other side. It's going to cancel that out completely. That's what I was going to do. And in this term, it's actually going to do 1.5 over 3.5. It's actually going to be a half. So we got a half there. So it's 17 kilograms times, we're just going to write it out that way. We're going to write it as 17 kilograms plus 1/2 times 50 is 25 kilograms times 9.81 meters per second squared. 42 kilograms times 9.81 meters per second squared. And we're going to get, that's a meter right there. The meters were still carried through. We still had our meters that were carried through. The 3.5 went away, but the unit of meter didn't go away. And the unit of meter didn't go away here. So we've got a meter that's still carrying along as our units. Got to be careful with the units like that when we want to try to go fast this way. So we got 42 times 9.81 times 1 meter, basically the unit of meters, is equal to 412 Newton meters. Okay, that's the tension. The tension is just going to be the meters. Good grief, what am I doing? The meters didn't stick around. The meters canceled out with the 3.5 meters that was on the bottom. It's just 412 newtons. That's what you got. 412. You can tell it's the end of the day on Friday, right? It's like, so it's 412 newtons is the tension in the cable. Again, we divided 3.5 meters by 3.5 meters. The meters canceled out with the 3.5, and the meters canceled out there. I looked back and was not paying enough attention to what we were doing right there. So that's great. We have one component of the tension. And then we can look at this and we can say, what's the x component of the tension? And what we can say is the tangent of theta is the opposite over the adjacent. So the tangent of theta is equal to T sub y over T sub x, like that. But the tangent of theta is also equal to 1.72 meters over 3.5 meters, is equal to 1.72 meters over 3.50 meters. Everybody see that? Do you see that the tangent of theta, it's the same theta for the physical dimensions, the linear dimensions of the setup of the beam and where the height to where the tension, the cable is attached to the wall. That's 1.72 meters and it's 3.5 meters. So theta has to be, tangent of theta has to be opposite over adjacent, has to be 1.72 over 3.50. So T sub y over T sub x also has to be, it's the same theta. It's the same angle, so you have the same ratio of the tension. That makes sense to you physically as you think about that. As that angle gets to be smaller and smaller and smaller, as this beam gets to be longer and longer and longer, or the attachment point of the tension gets to be lower and lower and lower, you're going to have almost all X tension, right? And that's what's going to happen here. If the 3.5 becomes 350, you have essentially very little of your tension is in the Y direction. Likewise, if this beam gets to be very short and this gets to be very tall up this direction, if this gets to be 0.035 meters, so you've just attached this thing a few centimeters out here, the beam distance is a few centimeters out here, then you have virtually all Y tension, just like you have virtually all Y component of your distances. So this all adds up. This all makes sense to us. So we can say T sub x is equal to 3.50 over 1.72 times T sub y, which is basically 2. I'll go ahead and plug it into the calculator, but we've got 3.5 divided by 1.72. 3.5 divided by 1.72 is 2.03 times 412 is equal to 838 newtons. Okay, so the tension is equal to T sub x squared plus T sub y squared, all square rooted. So it's going to be this number that I just calculated squared plus 412 squared, and then we're going to take the square root of that, and it's going to give us 934 newtons. So we got the tension was 934 newtons in the cable. So the cable's doing a lot to hold up this beam and this bag that's out here. The next step in the process, if we wanted to make this problem more interesting, is let's imagine that the maximum tension this cable could hold is only 2,000 newtons. Okay, suppose the tension is 2,000 newtons. We're not, we're a factor of 2 safe of breaking this cable right now. But imagine this is a bag of goodies, a bag of treats, and there's a bear. Look at that fabulous bear that I've drawn. And there's a bear that's walking out this direction. The question is, how far can the bear get out there before the cable breaks? Because you got this big, I don't know, what does a bear weigh? Let's have this bear be, it won't be a huge bear. Let's have this bear be 300 kilograms. So a 300 kilogram bear that's causing more and more and more tension in the cable as it gets out this way, because it's causing more and more and more clockwise moment as it gets out there. At some point this is going to break. And then the bear presumably has a little parachute on its back, and it parachutes down to safety below and gets the food anyway. So that's the next level of the problem if you wanted to figure that out. So this is what we've got. We set the moments up. To do this, to find the tension, all we had to do was figure out that the counterclockwise moments were the same as the clockwise moments. Now we could go back. We have T sub x and we have T sub y, so now we know what the hinge forces are. So we could go back and calculate the hinge forces if we wanted to know that too, because they're sort of equal there. So this is this is of course not right. H sub x is T sub x. We were going fast here because H sub y also has to be equal to, depends on what direction we don't know what direction H sub y is, but let's assume that H sub y is down, and then H sub y would have to be equal to, H sub y is also in the same direction as the 50 kilograms times 9.81 meters per second squared plus 17 kilograms times 9.8. So that's all downward. That's the negative, in the negative direction. We can just assume that H sub y is in the positive direction, and we put this on the other side. The tension and the hinge force have to balance the downward weight of the beams. If we got the direction wrong, if we're assuming H sub y is up in this direction, if H sub y is actually down, when we solve this problem, we stick in T sub y, we're going to get a negative answer. So anyway, we go back. We didn't set the problem up to do that because we weren't planning on doing that. We were just going to get down to get the tension in the cable. But you see how we could do anything we wanted to do. Hope this is helpful. Hope this is helping you get along and do the stuff you want, to see why we set things up the way we did and how we can go about doing this. So the next time you see a problem like this, maybe you can work all the way through it without much trouble. So that's what we got. Thanks for watching. Have a good day.